We've been discussing functions of several variables. For us, several generally means two or maybe three. All interesting behaviors, though, are demonstrated in the case where n equals 2, so for now we'll restrict our attention to that case. For functions of two variables, f of x and y, we've done various things. We have defined the partial derivative of f with respect to x and of f with respect to y in terms of limits, as is customary. We have determined the meaning of these things. The first one is the slope of the surface z equals f of x and y in the x direction. The other is the slope of that surface in the y direction. Also, we've come to realize that because when I do the partial of f with respect to x, for instance, x is the variable and we treat y as a constant, while in the other one, partial of f with respect to y, I treat the y as the variable and x as a constant. As a result, every technique that we know from Calculus 1 for finding derivatives is on the table. For example, if the function in question is f of x and y equals x squared y cubed, and we want to find the partial of f with respect to x and the partial of f with respect to y, at the place where x is -1 and y is 2, for the first one, we will treat the x as though it's the variable, and the y cubed will be treated as a constant factor. In that case, the derivative is the derivative of x squared multiplied by the constant y cubed. That would be 2x multiplied by y cubed. In the case of the partial derivative of f with respect to y, x squared is a constant factor. The variable is y. The derivative of y cubed is 3 times y squared. So putting it all together, partial of f with respect to y would be 3 times x squared times y squared. If you put in now the values x equal -1 and y equal 2, you find out that the rate of change of the function in the positive x direction is -16 at the point we're speaking of, and the rate of change of f with respect to y in the positive y direction is 12. The function is decreasing at the point we're interested in as y is held constant and x is increased, while y moving with the x held constant produces a rate of change of the function, partial of f with respect to y, that is 12. In the positive y direction, the function is increasing at a rate of 12 units of function value per unit of y. In an exactly similar way, we can calculate the second partial derivatives. The first one, the second partial of f with respect to x, is the derivative with respect to x of partial of f with respect to x. The second partial of f first with respect to x and then with respect to y is the partial with respect to y of the partial derivative of f with respect to x. Second partial of f first with respect to y, then with respect to x. You differentiate with respect to x whatever it was you got when you did the partial of f with respect to y. Second partial of f with respect to y both times is the partial with respect to y of the partial of f with respect to y. We've already calculated the two first-order partial derivatives so that you can then insert them into each of these four expressions. The second partial of f with respect to x both times works out to be 2y cubed. The second partial of f first with respect to x, then with respect to y, works out to be 6 times x times y squared. the second partial of f, first with respect to y, then with respect to x, is the derivative with respect to x of the partial of f with respect to y, which works out to be 6 times x times y squared. Observe that the two mixed partial derivatives are the same. We've come to expect that. The second partial of f with respect to y is the partial with respect to y of partial of f with respect to y. The derivative, where y is the variable, of 3x squared y squared, that would be 6 times x squared times y. At the point of interest, inserting x equal -1 and y equal 2, we get these values for the four mixed partial derivatives together with the unmixed ones. The unmixed ones, partial of f with respect to x both times, this tells me the concavity of the surface in the x direction. Since this is 16, the graph is concave up in the x direction at the point -1, 2. Likewise, the second partial with respect to y both times is 12, which is positive. The surface, the graph that we're looking at, is concave up in both the x direction and the y direction. If a person didn't know any better, they would think that that guarantees that it's concave up in all directions, but as we're about to see, that's not true. If we calculate that d number, which told us the concavity of the surface, we find out that there are some directions that are concave up, but others that are concave down. So this is interesting. The partial of f with respect to x both times and the partial of f with respect to y both times, both being positive, is not good enough to guarantee that my surface is concave up. In this case, it isn't. Two comments that hardly seem worth making are, if you do an indefinite integral, the name of the variable is almost completely arbitrary in the sense that it doesn't matter what it is. And secondly, if you do a definite integral, then the first statement is true, but even more so, since the name of the variable doesn't even show up in the answer. I need to show you exactly what I mean by that. For that first comment, think about the integral of 3x squared plus 2x plus 1 integrated with respect to x. This is a simple calculus 1 problem. Everyone can clearly see that the answer must be x cubed plus x squared plus x plus a constant of integration. Suppose somebody worked a similar problem except the name of the variable was alpha instead of x. Following the same rules, the antiderivative is alpha cubed plus alpha squared plus alpha plus a constant of integration. These are the same answer, except for the name of the independent variable. So if you did the same integral except it was 3 gamma squared plus 2 gamma plus 1 integrated with respect to gamma, you would get the same answer because of the way the fundamental theorem of integral calculus works. And as far as the second comment goes, think about the integral from 0 to 4 2x with respect to x. X is the variable, and antiderivative for 2 times x is x squared. I evaluate that between x equals 0 and x equals 4, and end up with 16 for an answer. Think about the definite integral from 0 to 4 of 2 alpha d alpha. An antiderivative will be alpha squared. It's alpha that's 0 and alpha that's 4 now. But still, when I subtract the square of those two quantities, I get 16 again. In the third line, I've made up a nonsense symbol. It's a V with 3 underscores and a dot. That's the name of my variable. I'd like to find integral from 0 to 4 of 2 times this funny symbol integrated with respect to the values of this funny symbol. Antiderivative, you square the funny symbol, you substitute for its value 0 and 4, and end up with 16 for an answer. When you do a definite integral, the name of the variable doesn't show up in the answer. This is going to be a comment that will be rather useful to us. Because of those comments, the integral from 0 to x of 2x with respect to x doesn't make sense. If it did make sense, the variable of integration would not show up in the answer. But if you just mechanically follow rules without thinking about what you're doing, you would say, well, all right, x is the variable, and antiderivative of 2x is x squared. I'll substitute the value of 0 in for x, which by itself is harmless, but then I'll substitute the value of x in for x, get x squared minus 0 squared, which is x squared, and I will have found a definite integral whose answer depends on the name of the variable of integration, and as we just saw on the previous page, that's no good. So this doesn't even make good sense. So you can make a long list of words in various languages that express our displeasure at having written such a thing. This makes no sense. Don't ever write something like that. By way of analogy with partial derivatives, when we write something like integral of 6x squared y with respect to x, what we mean by that is a function of two variables whose partial derivative with respect to x is 6x squared times y. And when we write integral of 6x squared y dy, we mean a function whose partial derivative with respect to y is 6x squared y. Really, we should write curly dx and curly dy here, but no one does that. This is the standard notation. So to calculate the integral of 6x squared y dx, I think to myself, x is the variable and y is being treated like a constant. This means that the factor 6y is a constant factor within this context, so I can pull it out of the integral. The integral of x squared with respect to x is x cubed over 3, so my result is going to be 6y multiplied by x cubed over 3 plus something that plays the role of the constant of integration. The differentiations involved for this particular part are derivatives with respect to x, so by constant, I could mean an actual constant like 7 or 14, or I could mean some quantity that's constant with respect to x, doesn't have any x in it. It would be all right for the constant of integration to depend on y, though. So my partial antiderivative is 2yx cubed plus some function which may be constant or may depend on y, but not on x. Checking that, the derivative with respect to x of our answer, the derivative of something that only depends on y, when I'm varying only the x, is 0. 2y is treated as a constant factor. Derivative of x cubed is 3x squared, so we end up with 6x squared y, which is what we wanted to end up with. If we integrate thinking of y as being the variable, though, now 6x squared is the constant factor, which can be pulled out of the integral. Antiderivative of y with respect to y is y squared over 2, and then given one partial antiderivative, I add the constant of integration, b of x, this being constant with respect to the y variable. You get 3x squared y squared plus some unknown function of x only, b of x. As a sanity check, take the partial derivative with respect to y of your answer. 3x squared is a constant factor. The derivative of y squared with respect to y is 2y. Derivative of something that only depends on x with respect to y is 0, and you end up with 6x squared y, just as you're supposed to. So, for example, you can look at several different types of integrals. You could look at the integral from 0 to x of 2y plus 1 dy. Y is the variable of integration. The y must not show up in the bounds of integration, and it doesn't, so everything's fine. Integral with respect to xy with respect to y, integrated from y equals x plus 1 to y equals 2x plus 4. The variable of integration is y. Y does not appear in the bounds of integration, so everything is fine again. This one is no good, though. The integral of 2x with respect to y must not show up in the limits of integration, but it does in this case. This doesn't even make sense, and the integral from x to y of x minus y dx means that since x is the variable of integration, it can't show up in the bounds of integration, and it does. So these two don't even make sense, but these two do make sense. We'll go on and calculate the two that make sense. So firstly, the integral from 0 to x of 2y plus 1 dy, we'll just use the antiderivative method. If y is the variable, an antiderivative is y squared plus y, and it is y that I have to put the value 0 and x into to subtract. Because I've got more than one independent variable now, this could become confusing, so I'm literally going to say I'm going to make y 0 and make y equal to x and subtract. So we'll have x squared plus x minus 0 squared plus 0, which is x squared plus x. Generally speaking, if you integrate from a function of x to some other function of x, f of x and y, with respect to y here, I just realized that looked an awful lot like an x. I'm integrating with respect to y, then what comes out, generally speaking, will be some function of x. Likewise, if you integrate from some function of y to some other function of y, some integrand f of x and y, integrated with respect to x, what comes out is a function of y only. If we want to look at the integral from x plus 1 to 2x plus 4 of xy integrated with respect to y, x is being treated like a constant, and antiderivative for y is 1/2 y squared, and to do the antiderivative method, I put y equal x plus 1 and y equal 2x plus 4 into the antiderivative and subtract. I factored the 1/2 x out to get it out of the way, and assuming that I've done all of my algebra correctly, the value of this integral is 3/2 x cubed plus 7x squared plus 15 over 2x. if I integrate from some function of x to some other function of x, a function of x and y with respect to y, what comes out is a function of x generally. If I integrate from some function of y to some other function of y with respect to x, generally speaking, what comes out is a function of y. So these are things that we know how to integrate if we know about Calculus 1. If you integrate from some function alpha of x to some other function beta x, f of xy with respect to y, then we've figured out that that is just going to be a function of x. If a and b are actual numbers, I can integrate a function of x from x equal a to x equal b. That is to say, at least conceptually, the integral from a to b with respect to x of the integral from alpha of x to beta of x with respect to y of f of xy will just be a number. We're going to be very interested in that kind of number shortly. Alternatively, if L of y and u of y are functions of y only, I could form the integral from L of y to u of y of f of x and y integrated with respect to x this time. There mustn't be any x in the answer, so that has to be a function of y only. If c and d are actual numbers, then I can integrate a function of y from c to d and get a number out of it. The other kind of iterated integral that we might look at is the integral from c to d with respect to y of the integral from L of y to u of y, L and u are for lower and upper, of f of xy with respect to x. This should come out to be a number that doesn't have x in it and doesn't have y in it either. As an example of this, let's look at the integral from 1 to 2 with respect to x of the integral from x to 3x squared with respect to y of 6 times x times y. Before we begin, let's just make sure that things make sense. This inside integral is being done with respect to y, and y does not appear in the limits of integration. So assuming that we can do the antiderivative of this, we will substitute in two different expressions involving x only for the y. The result will depend only on x. We'll be left with the problem of integrating from 1 to 2 with respect to x, whatever function of x this works out to be. The inside integral is the integral from x to 3x squared 6xy dy. Since we are integrating with respect to y, the 6x is regarded as a constant factor, and antiderivative is 6x times y squared over 2, that is to say 3x times y squared. I write the 3x factor outside. I'm going to square 3x squared, subtract x squared, and then multiply by the 3x. Assuming I've done my arithmetic correctly, the result is 27x to the 5th minus 3x cubed. As predicted, there is no y in this anymore. There's only x. Consequently, this is a function that I can integrate from a constant value to another constant value with respect to x and get a number out of it. To finish the calculation of the iterated integral, I now have to integrate from 1 to 2 with respect to x, 27x to the 5th minus 3x cubed. This is now a routine Calculus 1 problem. Find an antiderivative, put x equal 1, x equal 2 into it, and subtract. Assuming that I've done my arithmetic correctly, the resulting value for the iterated integral is 272.25. So, assuming that we can do all of the antiderivatives involved, the mechanics of calculating one of these iterated integrals is now clear to us. What is not clear is why a person would want to do this, and what sort of applications could such a thing apply to. That'll be the next thing that we talk about when we talk about double integrals and Fubini's theorem. In the meantime, our storm appears not to have materialized, at least not yet. I hope everyone is having a good evening. Stay safe, and we'll talk again soon.